Question about the exam. What is the syllabus? Everything that we covered till today?
No, till the 3rd. So today, next week, there's still one more lecture. So it would be everything we cover through the 3rd. I'm hoping to finish functionality and start enzymes today and finish it next time. So everything until enzymes.
And will you ask us to draw structures? I noticed that practice problems have structures,
Yes.
but how would we
Yes,
like?
that's why we practice. Oh, shoot. You're right, Redika. How are we going to do this? Sorry, I had to bring.
Yeah.
Oh, man. Then there won't be structure. This is so sad. Yeah, no. I will modify, make sure there's no drawing involved.
Thank you.
But you need to know the structure because I will be asking, I will change any question that requires drawing to you telling me the functional groups or the R group. So you want to know how many carbons, how many amines group in the R group. So I need you to know the R groups. I will modify any question I have to have you state the R groups instead of drawing them. Okay, good question. Thank you, Radhika, for asking this question. All right, any other questions regarding the exam? I appreciate most of you are working on those practice problems. If you haven't been doing that, I encourage you to do that as you study for the exam, because it's practice. That's why I give them. It's not really for grade reasons, it's for you to practice and be kind of sort of prepared. There is another set of practice problems that I put up. That's practice number 3. It's related to denaturation and functionality. So, but it's not due until not this Sunday, the 7th, until March the 7th. So you have time. So again, I will unlock the key for practice set 2. And I just did that now before I forget. And then once after Sunday, on Monday the 8th, I will open the key for practice set 3. Okay. Any other questions? All right. I'm gonna share my screen. All right. So we'll start with recap. I barely started with functionality, just giving you, like we had a couple of questions and a couple of FYI table, but let's review a little bit protein denaturation. So can somebody define protein denaturation? Any brave soul?
Is it the loss of secondary and tertiary structure?
Yes. So protein denaturation is any modification to the protein structure that causes changes in either quaternary structure. We can have dissociation at different external conditions, pH, salt, and temperature. Or we can have unfolding of the tertiary structure by breakage of internal bonding. Or we can even have changes on the secondary level where alpha helix, for example, changes to beta sheet, and some of the alpha helix beta sheet convert to random coil. So that's also protein denaturation. Even changes in the primary structure, like if we have hydrolysis of some peptide bonds, that's also protein denaturation. In simple term, unfolding of the protein. So you kind of hear it mostly as protein denaturation as unfolding of the protein, but it's beyond that. But in simple terms, it's unfolding due to breakage of some internal bonds due to external environmental conditions. So breakage of few bonds can lead to kind of a sequential denaturation because you get a lot of entropy. So there's a change in entropy. So you have chaos and lots of energy, and then that might also cause breakage of more bonds. And therefore you get delta G negative. So, all right, so that's protein denaturation. How does amino acid composition affect the protein thermal stability? What do you remember we talked about amino acid composition or even structure that impacts thermal stability? Anything you remember or any example that you can give?
Hydrophobic bonds are strengthened with temperature. So a protein that has higher amount of hydrophobic amino acids will have a higher denaturation temperature, and
That's a
vice versa for hydrogen bonds.
That's good. So when you have amino acid composition that has tendency to form hydrogen bonding and form a structured secondary structure, so alpha helix, beta sheet, and you have a very structured configuration, like a globular configuration versus an open structure configuration, then you have lower denaturation temperature. Also, amino acids that tend in the composition that tends to form, or in the sequence that tends to form alpha helix versus beta sheet. Alpha helix are more thermally labile than beta sheets. So amino acid composition and sequence impact secondary structure, tertiary structure formation, and therefore the thermal stability. For example, in casein, specifically amino acid that is proline, you want to remember that, it's really high in proline. 17% of the amino acids in caseins are proline. So they're secondary structure breakers. So you don't really have a structured secondary structure. You don't have a lot of alpha helix, beta sheet. You have more of a random coil and rather open structure. So that form of a protein has high denaturation temperature. And also caseins, we'll learn about them later. They form quaternary structure, the casein micelles, and they are stabilized by hydrophobic interactions, so that it's not easy to kind of denature them within that quaternary structure as well. Okay, so how does water facilitate thermal denaturation? Can anybody remember the impact of water on protein denaturation? Low water concentration, high water concentration, how does that impact denaturation? So protein in solution versus dry protein powder. Which one would have lower denaturation temperature? Come on, guys, you should know
water,
this.
like water would expose more the groups of hydrogen bonds, and then will have a high will denaturate faster in solution.
Yes, thank you, Son. Yes, so the presence of water facilitates thermal denaturation. So the more water you have, so you have more thermodynamics and movement of the water. Water can go into the interior moiety of the protein, causes hydrogen bonding to break within the protein molecule, and rather have hydrogen bonding with the water. So breakage of a couple of hydrogen bonding again increases the entropy, and then with an increase in entropy, denaturation becomes spontaneous. So the more you have water, the lower is the denaturation temperature. So the most stable form of the protein is dry protein powders. But how much moisture content is in the dry protein powder also impact their denaturation. Okay, so why high protein concentration may result in irreversible denaturation upon heating? So if we're saying 1% protein versus 5% protein.
Because of protein-protein interactions or covalent bonds, disulfide bonds being formed?
Sure. So the more protein you have in solution, and when you start heating, the more they're going to be movement. And if there are a lot of them, they're going to be more tendency for them to get in close proximity to form hydrophobic interactions. And hydrophobic, they come together via hydrophobic interactions. But if you have free sulfidyl group, that will also facilitate disulfide interchange. And once you have disulfide linkages with strong hydrophobic interactions, that is an irreversible form of interaction and denaturation. So it's very hard to break these covalent bonds naturally. They do have a high rate of equilibrium. So you cannot go back easily. Okay. Can you think of denaturing agents and how they could denature? So think of one and how.
And an enzyme like rennet, which
Yeah.
cleaves the casein and denatures it so that it coagulates.
Yes, absolutely. So enzymes. So we learn more about how kappa casein is broken by the enzyme later on when we cover daily proteins. But yeah, the glycomacropeptide that stabilizes the casein in my cell get hydrolyzed by chymosin, and then it breaks out the whole stability of the system. Okay, what other denaturing agent?
Urea or acetone?
Yes, so detergents and organic solvents. So SDS, urea, beta-mercaptoethanol, like reducing agent, these can cause breakage of bonds. And these breakage of bonds, again, leads to high entropy and then denaturation. Also organic solvents. Why? Because the nonpolar R chain of the amino acid will become more soluble with the solvent. So that means that the protein will start opening up, and instead of hydrophobic interaction within each other, they start having hydrophobic interaction with the acetone or the organic solvent. Okay, what are some common methods used to assess degree of denaturation? Can you remember any of the methods we talked about?
You can use UV absorbances.
Yes, we can use UV absorbance because when the protein denatures or unfold, you're exposing more of the aromatic amino acids that are nonpolar and potentially would be in the interior. So you increase absorption and you increase fluorescence. So that's a good method. What else?
DSC.
Yeah, differential scanning calorimetry. It gives us a couple of things. It gives us the temperature of denaturation. If the protein is not yet denatured, it tells us at what temperature it would denature. And also it gives us the enthalpy, change in enthalpy. So how much energy was needed to unfold that protein. And if we don't see any endothermic peaks, so no change in enthalpy, nothing comes out straight line, that means your protein is being completely denatured already when you're testing it. Okay, what else?
Protein digestibility.
Protein digestibility. It's a good index. It really, you have to start with a protein that is not denatured, so you know what the digestibility is for that, and then do the digestibility, because sometimes digestibility enhances upon partial denaturation. You see an enhancement in digestibility, but when you have a lot of denaturation and polymerization happening, so irreversible denaturation, then digestibility decreases. So we really always, when we measure digestibility as an index of denaturation, we really have to have our controls, like a non-denatured protein. Good. What else?
FDIR.
Spectroscopy.
So what spectroscopy?
Spectroscopy, circular dichroism.
Circular dichroism, yes. CD spectroscopy gives you secondary structure information.
And tertiary also.
And okay.
If we work in the near part, certain structures, if we work in far, secondary structure.
Okay, and then you also have FTIR where we can get amide 1. And with that, you can deconvolute and get secondary structure, and you look at alpha to beta sheet ratio, and you look at increase in random coil. Perfect. What other than spectroscopy?
Is it OPA as well?
So OPA is usually a method to determine free amine. So we don't usually use it to determine level of denaturation. You actually, in OPA, sometimes you add SDS in the procedure. So you already denature the protein, so you can measure all free amines. So not really.
Can you say, for example, when a protein loses its some functionality, is a degree, we can assess degree of denaturation?
Yes, I was going to say solubility specifically. So when we see a decline in solubility, that's an indication of denaturation as well as irreversible denaturation. Very good. And we also have other types of spectroscopy like Raman, surface enhanced Raman spectroscopy can also show us differences in tertiary structure and changes in bonding that would indicate denaturation. I think we covered more, or if we have an enzyme, we can measure the activity of the enzyme as well. So yeah, so that's great. So try to remember these different methods in case you were asked to give an example and you want to be able to explain it and say, how does it tell us if the protein is denatured or not. One of you said SDS page, and with SDS page, it really tells us the irreversible denaturation when we form polymers. So it doesn't necessarily tell us if the protein just unfolded, because anyway, with SDS page, you are adding SDS, you're denaturing the protein. But it does tell us if there is covalent interactions that occurred, like disulfide interchange, because you can run the gel under reducing and non-reducing conditions. So you can see under non-reducing, you have polymers. Under reducing, these polymers go back to monomers. You know that, oh, I got covalent disulfide interchange. Sometimes there are covalent interactions due to Maillard reaction, for example, advanced stage of Maillard reaction, that you see the polymer, but under reducing condition, you still see the polymer. It doesn't go down. So you know that it wasn't polymerization by disulfide interchange. So it's a very useful method that we use a lot to assess polymerization and how the proteins, which forces or bonds cause the polymerization. Okay, so that's great. I'll move on to continue. Oh, any questions? Sorry, from last time or now or anything?
I had one, Pam. What is the difference between sequential denaturation and spontaneous denaturation?
Yeah, so spontaneous is due to the sequential, really. So basically one thing leading to another, and it occurs quickly, because what couple of bonds that are broken then can lead to more bonds breakage, and that happens quickly. Like it doesn't take a long time to happen. Yeah. Any other questions?
Yeah, the extra credit, the last question asked for 3 sequencing methods. I understand, I could think of 2 and I had to guess the third because I wasn't clear on the slides. So what would be those 3?
So did you say N-terminal sequencing, which is the admin sequencing?
Yeah, Edmund and Maldi.
Admin and Maldi, yes. What's the third?
The third one I guessed was mass spec.
Spectroscopy.
Say that again?
It's IR spectroscopy. IR.
It won't tell you the sequence of amino acid. So LC-MS can give you the sequence, but that's when you do ladder sequencing. Now I'm curious. Let me look at the key.
I thought it was because it asked for structural and sequence information, so it doesn't have to be all 3 of them sequence, right?
Oh, is that the question? Let me look at the question then.
Yeah, she's right. That's what it's asking.
Identify full name. By full name, 3 techniques that could be used to obtain structure. Oh, structure and sequence. Yes. Okay, so now that makes sense because I couldn't think of a third sequencing because it's MALDI is mass spectrometry, and then you do ladder sequencing, and then you are the admin sequencing. But for structural, you can list a lot of different methods for structural. Yeah, so I was like, I thought that I am missing something. Good, I didn't lose my mind yet. Okay, any other questions?
Yeah, the clatherate, CLATHERATE. What is that again?
Say that again.
It's one of the slides. It's CLATHERATE.
Can you type it in the text? I'm not following. Can you type it in the chat box? Where is my chat box? Again, I can't see my chat box. Oh, okay. So this is basically just a description of the structure of the water. When you use forms like ice-like structure. So the drawing next to it kind of illustrated. So it's just the form of water that is formed around the protein.
Okay.
Okay. Any other questions?
All right, and then the last one.
Yes, go ahead.
So about NMR, this falls under the sequencing question. The NMR slide.
It's NMR, it gives you tertiary structure of the protein.
That's what I gathered, but there was a part of that slide says sequencing. I can't find it now, of course.
Are you looking at the NMR slide? Let me open it so that I can look at it as well. It's taking a minute to open. I'm not sure if it can give you sequence.
I don't think so. Just the word sequence is there, so I wanted to make sure I understand why it's there.
Oh, it could be just the title. Let me just see before I say anything.
Yeah, that little picture in the middle.
Oh, well, it depends. Yeah, I'm not sure if it actually gives you the sequence or it's just giving you how they are formed into tertiary structure. I don't really know a lot about NMR, to be honest. So don't put a lot of stock into this. I would just, if NMR comes up, it would be for molecular configuration. I'm not sure. I have to look up if sequencing is possible through NMR. I don't have experience with that. I will look it up and get back to you next time.
Okay.
All right. Any other questions? Okay. All right. So that's that. The other two in gray are related to what's coming. It depends on when I stopped last time. Okay, so we're going to go on and talk about functional properties, but I want to categorize the functional properties into 2 groups for you. So there is the functional properties that go under something we call hydrodynamic dash aggregation. So water is involved. So you have protein water interactions, and then you have protein water protein interactions happening. So all of these functional properties have water that takes part in the final structure or texture. So if the protein is soluble, that means there's no protein-protein interactions. There might be soluble aggregates, but mostly your proteins interacting with water so that they remain in solution. And then when we talk about water holding capacity, so the water is entrapped within a 3D dimensional or three-dimensional network, which is the gel. So there is water interacting as well with the protein, but by physical means being entrapped. Viscosity, you have water, protein, water interaction. So protein, water, protein interaction, excuse me. Also elasticity and viscoelasticity, you have water involved in the formation of this elastic structure. And of course, gelation, coagulation, where there is also water involved in the formation of the matrix. So the other category is, we call it the surface activity category, hydrophobic or surface activity in general. So the functionality that go under this category are the emulsification. So when you have an interface, two different phases that need to interact and remain in a stable form. So you rely on the surface properties of the protein and their hydrophobicity as well as their hydrophilicity. Same with foaming and flavor binding, because a lot of the binding with the flavor is via hydrophobic or sometimes hydrogen bonding. But of course, there's also covalent bonding. But a lot of interactions can be via hydrophobic interactions between flavor and protein. So in terms of what structural characteristics impact these functionalities. So in terms of the size of the protein, how large is the protein, and the configuration of the structure, as well as not just tertiary structure, but also quaternary structure. So these kind of characteristics of the protein control the viscosity. So the larger the protein, the more you have quaternary structure, the more you can form viscous solution or whatever, viscous matrix. Same with gelation. The larger the protein, you can see that proteins, we'll talk about gelation in a minute, but proteins that are usually larger than 23 kilodalton, with then they have tendency to form stronger gels. A thickening and texturization. Texturization, for example, soy protein and gluten protein are proteins that can form large polymers. So they can form, they have tendency to texturize better and give you meat-like fibrous texture than other proteins. Okay, the surface properties of the proteins also have an impact on the different functionalities. So the main surface properties, when we talk about surface properties, we talk about surface hydrophobicity and surface charge. So why are these important? They're important for solubility. So the more surface charge you have and the less surface hydrophobicity, the more the protein is soluble. Okay, so also it impacts water holding capacity. So if you have very hydrophobic proteins and really high disulfide interchange, for example, then a low charge, you really form kind of an aggregate thick, rather thick gel, but not really an elastic gel or a gel that doesn't have grittiness in it. Foaming and emulsification, of course. So if you have foaming and emulsification, you really need to have a balance. The protein cannot be just completely hydrophobic on the surface or really large hydrophobicity, no charge, no hydrophilicity. Then there will be very low interaction with the aqueous medium. And you don't want that. And also if you don't have, we'll show that when we talk about emulsion and form, but once you have a film around your oil or a film of protein around your air bubble, you want the protein on the surface of the film to carry some charge so that there is repulsion between the two oil droplets or the two gas air bubbles. So if you don't have enough repulsion, then they will coalesce, fluctuate, and cream sedimentation or creaming happens in emulsion, for example, or you lose the foam or the air in foams too. So it's very important to have a balance of surface hydrophobicity to surface hydrophilicity, which has to do a lot with charge as well, and polar groups, obviously, on the surface. So this is kind of like an overview of things, but then now we will dive into the different functional properties, and I will also relate structural characteristics to functional properties as we go. So interaction with water. So this is important because there's a lot of systems that depends on protein-water interaction. So I will give an overview of that. You all love isotherms, right? I don't like isotherms, but they explain a lot of things sometimes. And isotherm is the relationship between moisture content and water activity. And we do have 3 distinct regions that we will talk about with relation to the protein only. So water activity between 0 to 0.25 is monolayer and lower usually. So in that region, the water is strongly bound to the protein via dipole-dipole interaction and hydrogen bonding. So it's bound to the charged and polar groups very, very strongly. And this water is unfreezable. So that means it won't freeze. Once it's bound strongly to the protein, it won't form ice crystals. And also it's not available for solubilizing solutes or chemical reactions. It's not available for that. And also you require higher heat, more heat to evaporate it than the unbound water or the bulk water or free water. So if we look at this here, this diagram, it's just showing you that the protein without water, and then as you start adding water, you start seeing interactions with the protein. So when we go from B to C, we see partial water binding, but then also binding mostly with the hydrophilic and polar groups. The dark spots represent hydrophobic regions on the protein, but eventually water will also bind to hydrophobic groups or will form this ice-like structure around these hydrophobic groups. And slowly and gradually you form the monolayer of the water around that protein. So the region 2 is kind of like completion of the monolayer and start to build a multi-layer water. It's the beginning of adding multi-layer water around the protein. And that multi-layer water will be available for dissolving solvents if you have salts or sugars, and also chemical reactions. And anything above that is more multi-layer water, more free water, basically free-flowing water available for reactions as well. So with that, I want to introduce certain terms that you'll come across. So we talked about strongly bound water. These are strongly bound by dipole interactions and hydrogen bonding, so that these will lead to the formation of the monolayer. So this water that is bound, it has different characteristics than free water, so that which we talked about needs higher temperature to evaporate, does not freeze, not available for chemical reactions. And then you have a term that we call entrapped water, and this is the physically entrapped water. So we have bound water, and then we have physically entrapped water. So this is entrapped in the in its three-dimensional structure or a structure matrix, a protein matrix, and is not flowing freely. So like the gel, so you trap the water and it's not flowing freely unless syneresis happen. And then you have the free water that basically is, hydrodynamic water or free-flowing water that is available for reactions, not entrapped and just there. So what we hear a lot about two functionalities. We hear about water binding capacity and we hear about water holding capacity. And we'll talk about water holding in relation to water binding in a minute. But they're two different things and they should not be used interchangeably. There are a lot of literature out there that uses these terms interchangeably, and this is wrong. So if you see in a manuscript water binding capacity and they describe it as the water that it's physically held by the gel, this is wrong. So you want to know that this is wrong. But there's a lot of confusion out there around water binding versus water holding. So with water binding is actually the amount of water that is bound or retained by the protein under specific conditions, like interacting with the protein, basically. So there are different factors that affect how much water can be bound to a gram of protein, for example. The composition, which is amino acid composition. So there's this equation that relates how much water is bound per gram of protein to the composition of the amino acid. So the first fraction that you see that has a 1 factor of 1 or an A value of 1. This is, let's say this is A, B, C. So an A value of 1, that means it has the most impact on the amount of water that can be held by 1 gram of protein. And this is the charged amino acids. Following it are the polar amino acids. So it's a fraction of 1.4. So it has less impact on the grams of water, total grams of water per gram of protein. But polar amino acids, even if they're not charged, they also bind water. Even hydrophobic groups can also bind water. Some of the functional groups on the hydrophobic amino acids may form dipole interactions or hydrogen bonding, but much less than a polar amino acid or a charged amino acid. So you don't have to remember the numbers, but you want to remember that the impact of charged residues is higher on binding water than polar amino acid, than hydrophobic amino acid. So other than composition, the conformation. So whether is it a native protein or a denatured protein? You might be surprised to learn that denatured proteins will bind more water. Why? We exposed more groups. We have higher surface area now. So yes, it'll bind more water. Temperature. So remember hydrodynamic, thermodynamic, I want to say. So with higher temperature, you have tendency to bind more water. pH. So if you change the pH and you end up having more ionizable groups, then you will, of course, bind more water with more ionizable groups or ionized groups. Salt concentration. So it really depends on the type of salt and the concentration. So a little bit of salt can help with increasing the interaction with water by increasing the charge load on the protein. But a lot of salt can actually shield the charges on the protein, preventing water interactions. So depending on the concentration, we talked about that before. And also the type of salt, is it a cosmotrope or a chaetrope? So you want to remember the difference between these two. Chaetrope are types of salt that bind loosely to the protein and enhance protein-water interaction, whereas chaetrope bind very strongly to the protein and reduces the ability of the protein to interact with water. And there's also the presence of low molecular weight like sugars that actually act as cosmotrope. So they bind loosely to the protein and they're polar. They enhance protein-water interactions. Here are some illustrations of temperature effect and how it varies between different types of proteins. And I'll explain why it varies. So if you look at casemates, no matter how you increase the temperature up to 100 degrees here, potentially, you don't see a change. Can one of you tell me why? Or anybody tell me why? Do you think? Think about denaturation.
The globular structure is more stable.
The globular structure are less stable, right? You got the right kind of idea about the structure, globular versus open structure.
Probably because of interaction between different residues. When we when we increase the temperature, the structure is unfold, so we have higher water binding, but from a specific point. After that, we have, because the hydrophobic residues are superimposed, they are prone to have interactions with each other, hydrophobic protein interactions. It causes reduce in water holding.
So in this case, we don't see an increased water holding or a decrease in water holding really over temperature for casein, because casein does not
water binding.
135 degrees Celsius. So if the protein is not changing in structure, so with temperature, there's nothing that would impact the protein to absorb more water. So if we look at, so there's no uptake, more uptake water, there's no change in structure, nothing is really happening. So the temperature is not causing anything to happen to the casein, so we don't see a change in water binding. If we look at whey protein during the nature around 70 degrees, right? So after 70 degrees, we start seeing an increase in water binding until we reach a plateau, because nothing is happening beyond that. The protein denatured, it bound as much water as it could be in that denatured state. If we look at soy protein, I don't know why it's called SPS. It's supposed to be soy protein. So when you look at soy protein, also we start seeing denaturation above 70, between 75 to 85 degrees C, we have denaturation, and it's a very globular structure too. So we see an increase, and denaturation may start at lower temperature, but it will peak at the denaturation temperature of most of the proteins in that particular isolate. And then you see a decrease, and you might wonder, why do I see a decrease? Because beyond certain point of denaturation, this particular protein starts to aggregate. So you start seeing protein-protein interactions more than protein-water interaction. So we start seeing a decline. So different proteins behave differently based on their impact, how they change in structure based on the temperature. This is the salt effect. So basically what this is showing is, with increasing salt concentration, we start seeing like kind of the salting in effect. We start seeing more water interaction, but then it plateaus. If they increase the concentration beyond 1.2, we would have seen a decrease, but this did not go beyond 1.2. It just reached a plateau, but we know that after certain concentration, we will start seeing decline in water binding. pH is like in solubility, similar kind of curve looking impact. So the more ions, or the more ionized the more functional groups are ionized, the more you have binding. So at acidic pH, we have more positive charges, so we have more binding. At around the close to isoelectric point, where you don't have a net charge, you have less binding. And as we increase the pH, of course, towards alkaline, we get more binding. But why do you think we have more binding at alkaline than at acidic in general, and regardless of the type of protein?
Is it due to certain amino acids like tyrosine and cysteine? They
Yes.
they get charged at alkaline pH.
Absolutely. So those proteins that have OH group and SH group at alkaline pH, they become ionized as well. So it's not just the amine groups and the carboxyl groups, but these groups get ionized at alkaline pH. So perfect. Yes, that's why we see a little bit more binding at alkaline. And that's why we also see more solubility at alkaline conditions than at acidic conditions. Very good to remember that. And now, what's the difference between water binding and water holding? That's my introduction here to you, is that they're not interchangeable, and we need to understand the difference. So water binding is the actual binding of protein and water via hydrogen bonding or dipole interactions. Water holding is the holding of water within a matrix of protein, like in a gel. So how much water is entrapped, the physically entrapped water. Okay, I'm gonna give you a break now, 5 minutes. We'll come back at 3:55 to continue with the different functionalities. Okay, let's get back. I think we passed the 5 minutes break. I just got distracted myself. All right. Bringing everybody back. Good. All right. And I got distracted. I think Paul was asking this question by looking at NMR. And NMR cannot give you the sequence of amino acids. So I was reading just about it. I don't know, is Paul here? Paul asked this question?
Yep.
Yeah, okay. So NMR does not give you a sequence. It cannot assign amino acid to the different signals. It says specifically that you really need to know the primary structure of the peptide or the protein you're analyzing. So you have to come to NMR knowing the primary structure, that means the sequence. And then by solving the, looking at the spectra and doing the puzzle, I always call NMR spectra as puzzle, then you can assign amino acid to the different signals and then build the structure that way. So it's much more complicated than I'm stating, but just to answer your question, we cannot sequence amino acid by NMR. All right, so.
Alrighty.
Okay, good. So, and also I remembered that there was last time, there was a question from one of you about digestibility and reporting PDCAS on the label. And how do we have regulations? And I answered last time, it's like, there's really no regulations I know of, and everybody reports it the way they find most appropriate. And then serendipity happened, and then I got a call from, or a request to answer a few questions from Schwann's. So their nutritionist specialist was asking me about amino acid composition and score and how we can calculate PDCAS. And then I helped her answer the question of calculating PDCAS and digestibility. And she said, well, do you know, we can't find regulations around digestibility and protein processing and digestibility. And I said, well, welcome to the crowd. So even like industry, they really don't know, they can't figure it out yet, and we don't have regulations. So it's really up in the air and requires regulation. So this is just confirming that there is no regulation in determining PDCAS, whether taking into account processing and effective processing on digestibility, or even the more interesting question she had for me is that when she's determining the amino acid score, does she use the protein that we get from CalDAL, or do we use the protein amount we get by adding up all amino acids? And I said, well, no, you have to get the protein content as you add it up by amino acids, because CalDAL is a crude method of protein, and you're determining nitrogen that is non-protein nitrogen. And also you're using a random factor, which is 6.25. which is not necessarily the correct factor for every type of protein. So I thought this information would be nice to convey to you as well, in terms of specifically PDCAS and how we calculate the amino acid score and what protein content we use. And just to remember that CalDAL is crude, DUMAS is crude, and we're not necessarily only looking at nitrogen from protein when we calculate based on DUMAS or CalDAL. So I thought that was nice to bring it to you since that conversation happened last week. Okay, let's continue where we left off. Go back here. All right, solubility. Solubility is the best functional properties. Why? It is very important for the protein to be soluble to function. If the protein is not soluble, it's going to really sediment and not form a gel if you're trying to form a gel. It won't form an emulsion if you're trying to form an emulsion. It's going to aggregate rather than go to the interface and form a nice film around your oil or air droplet. So solubility is important, and it is influenced, like I said, influence other functionality. And with higher solubility, you get better gels, you get better foams, better emulsion. You can use it for high protein beverages. And with less solubility, less overall functionality. But one thing I want to point out here is texturization does not necessarily require protein to be completely soluble in water. Actually, a completely soluble protein is not helpful for forming a protein structures, fibrous structure. So gluten, for example, is not soluble in water, but it forms it's very nicely texturized. So so there is kind of like this fine line between a protein being completely soluble versus you want it to function in a certain way. So there is always a balance that we need to remember as well, depending on the final structure we want to form. But yeah, so solubility, though, in general of the protein is important. Like we talked about earlier, it can be used as index of denaturation because solubility is reduced when the protein is denatured. There will be more protein-protein interaction and less protein-water interaction. And of course, it is dependent on extrinsic factors or environmental factors, such as the concentration of salt. Sometimes a little bit of salt helps. pH, so is the pH away from the isoelectric point or close to the isoelectric point? That means does the protein carry charge or it doesn't carry charge? And temperature. Sometimes a little bit increase in temperature helps with solubilization, but temperature above the denaturation leads to actually reducing the solubilization. So when we think about solubility and then the surface properties of the protein, we say that the more hydrophilic the protein is on the surface, the more it's going to be soluble. And the less charges, the less solubility, of course. So the more charge there is, the more polar a group there is, then there is more solubility. The more hydrophobicity on the surface, the lower is the solubility. So both, when we talk about solubility, both properties have bearing on solubility. How much there is surface hydrophobicity versus how much there is charge and polarity on the surface will impact your solubility. Sometimes there is high charge, but because there is high hydrophobicity as well, then they kind of counter each other. So when you measure one attribute, when you measure charge and you say, oh, the protein has net 30 charge, net negative 30 charge. So, oh, that should be very soluble. But if you look at its surface hydrophobicity, then it's high too. So then these might counter each other. So that's what it means when we say surface hydrophobicity and surface hydrophilicity both have direct bearing on protein solubility. So remember that. We talked about this phenomena when we were talking about extrinsic factors that impact a protein. So here in this case is in context of solubility, so not necessarily denaturation. So in this case, a little bit of salt helps the protein to solubilize, like we said. So a little bit of salt here kind of add a charge to the protein, maybe prevent electrostatic interactions between protein. If you have some salt, you have more water interaction with the protein rather than protein-protein interactions. So salting in. So that's something that is applicable in beverages where they add phosphates, for example, to enhance stability and solubility of the protein in the beverage. Or we do that in protein isolation. So when we have a matrix of protein, starch, or fiber matrix, and we want to remove the protein from the other carbohydrate matrix, we add a little bit of salt and we solubilize that protein. So it can be used for different purposes. And here I just put the, when we say there is a difference between saying salt concentration and ionic strength, they both relate to the amount of salt, right? But the ionic strength take into account the concentration of each ion and the charge of each ion. So this is kind of I is the ionic strength. This is also FYI. Okay, so salting out then, so when we add excess amount of salt, then you can see here, you increase the solubility, you reach a plateau, which I showed you earlier with water binding, for example. So you reach a plateau, and then with more highly concentrated salt or higher ionic strength, you start getting interaction with the different ionized groups, and then you break intermolecular interactions that are electrostatic interaction within the protein. Instead, they're forming interactions, ionic interaction with the salt. So protein can get denatured, and then there will be less interaction with water because the salt is shielding the charge. The salt is competing for interactions with water, and then the protein gets denatured, and then you get more hydrophobic interactions, protein-protein hydrophobic interactions, and then they will not interact with water and they fall out of solution. Okay, please do interrupt for questions or clarification and let me know if I'm going too fast. Don't forget. Okay, pH effect. So also we talked about that a couple of times now, is when you have a really high pH or a really low pH, that means you have either net negative charge at high pH or net positive charge. So repulsion, better solubility. Around the isoelectric point, net zero charge, least interaction with water, you have the least solubility. So I'm linking here structure to function, and in this case, structure to solubility. So these are two different proteins, whey protein and plant protein. I get a lot of requests from industry saying, can we make this type of plant protein act as whey protein? And we can put them in clear beverages? And I go, no, we can enhance the solubility of plant proteins, but they will never act like whey protein. Why? There are structurally fundamental differences between these two proteins. So here is the structurally fundamental difference. So if you take whey protein, if you try to solubilize the protein at different pHs across the board, from acidic to the isoelectric point to alkaline, you see you almost have 100% solubility, regardless of the pH. But whey protein has an isoelectric point of 4.5, 4.6, around that, between 4.5 to 4.8. So, and you go, why? Because if you look at soy protein in this case, around the isoelectric point, poof, it's not soluble without heat. So both here is without heat. And you would say, okay, a non-denatured whey protein, a globular non-denatured whey protein, has very low surface hydrophobicity. It has only one pouch of hydrophobic residues on the surface, and it's very hydrophilic on the surface. Take soy protein, for example. It is not very hydrophilic on the surface. It has good surface hydrophobicity, really high in surface hydrophobicity compared to native whey protein. So even at the isoelectric point, you don't have enough hydrophobic interactions between proteins to bring them together. Even if you lose net charge, the main force of protein-protein interactions at the isoelectric point is the hydrophobic interactions. So if you have very low hydrophobic interactions on the surface, or very low hydrophobicity on the surface, you'll have very low hydrophobic interactions. So the protein remains soluble. However, heat the protein. So this is native. We heat it at 70 degrees, which is around the denaturation temperature of whey protein in general, the average. Even if you heat it for 1 minute, you have denaturation occurring. Of course, less than 10 minutes and 20 minutes. But once the protein is denatured, that means it's unfolded. You have more hydrophobic residues on the surface. And at its isoelectric point, no net charge and a lot of hydrophobicity on the surface, of course, you're going to lose solubility because you get hydrophobic interactions. So this difference without heat between whey protein and a soy protein is characteristic of the structure, not just the environmental conditions such as the pH or heat. Okay. So that is something to remember. And that's why when we try to formulate beverage at 3.4 pH, you have 100% solubility of whey protein isolate at 5% protein, which is the percentage at which you can, above what you can claim as excellent source of protein. So you can formulate a 5% protein beverage and claim an excellent source of protein. Whey protein, 100% soluble. It does have a short shelf life though, because over time it's pasteurized, 5% protein, it will aggregate over time. But at the initial production, you have 100% solubility. However, soy at 3.4, it's really close to its isoelectric point. It's just around here, right? So it's not soluble. You have 20% solubility. It's close to its isoelectric point, very hydrophobic on the surface. It's not going to solubilize. Pea protein is even worse. So that's plant protein compared to whey protein in terms of solubility. So we have to always remember to link structure to function. So what happens in this case is when you really, really want to formulate with plant proteins, then you start needing to add stabilizers. So then your ingredient list grows. So here's actually not an acidic pH, a neutral pH beverage without a stabilizer. Over a little bit of time, it's going to separate. Protein is going to sediment. But if you add stabilizers, so such as carrageenan, for example, for neutral beverages, it will stabilize it for a short period of time. So you can make a beverage from plant proteins, but it needs more stabilizers than you would for whey protein. And it does have a short shelf life, and it is limited on how much protein you can add, because the more protein you have, the shorter the shelf life is going to be. Not let alone flavor, which is a different story with plant-based versus whey protein. So here's another research-related example on effect of pH on solubility. So we have our whey protein. Before heating, it's soluble over a wide range of pH, like we just showed you in that graph. However, once you heat it, it kind of falls or drops out of solution at around the isoelectric point. But what we did is we glycated the whey protein. We covalently linked a carbohydrate to that protein, and then all of a sudden, it did not denature. The protein did not denature at these temperatures and remained soluble. So we tried to see what happened. Why did it remain soluble? So we looked at surface hydrophobicity. So again, I'm linking structure to function here. So what we did is we looked at the whey protein itself and then the protein that was glycated. And we looked at surface hydrophobicity over heating time, heating at, I believe, 75 over here. So we took 10 minutes increments and we looked at surface hydrophobicity. So the glycated protein, because we glycated, it started with a lower surface hydrophobicity than the original protein. And we saw that whey protein naturally is going to denature at 75, and as with more heat, more denaturation, and more exposure of hydrophobic interiors, so the surface hydrophobicity increases. With more heat, we see a decline in surface hydrophobicity. Can anybody guess why, instead of me telling you? So after heating it longer, the surface hydrophobicity decreased. Does that mean it became more soluble?
Is it because of aggregation between the
Yes.
proteins?
Thank you, Nigel. Yes, it is because protein starts to, form hydrophobic interaction, because now with heat, hydrophobic interactions are induced, and disulfide linkages also are induced. So then we get aggregation, then we see a decline in surface hydrophobicity due to aggregation formation. Now, if we look at the glycated protein, which showed excellent solubility, even after heating at the isoelectric point, we see a slight increase in hydrophobicity. You have partial unfolding, and then nothing happened. It just maintained structural rigidity over time, which explains why it remained soluble even at its isoelectric point, because surface hydrophobicity did not increase. And with the protein maintaining its compact structure, then you don't have much of hydrophobicity on the surface, regardless of the pH. Now you don't have that much interaction there. You don't have that attraction due to hydrophobic interactions. So we also looked at change in the isoelectric point, and we noticed that our glycated protein shifted. So it had a lower isoelectric point, which also explained why it remained also more soluble around the isoelectric point of regular whey protein. So basically you want to keep in mind, when you want to understand why a functionality changed, a lot of the explanation has to do with how the structure changed, how the surface property changed, how the physical chemical characteristics changed.
I have a quick question. Oh, sorry.
Oh, no, go ahead.
Considering the glycated proteins, what would play like a bigger role, like spatial, like stereo influence of the glycated groups, or the net charge that would be changing? Like, what would be more important on this situation?
That is an excellent question, and this would be an example that I'll be talking about when we cover protein modification. Both. So you have steric hindrance from the bulky group of a carbohydrate, and you do also have less attraction, protein-protein attractions due to unlike charges or hydrophobic interactions. So you have multiple factors that play a role. So the steric hindrance is a big part of it too, but also the structure of the protein remaining kind of globular rather than open structure is also a big factor. So both. Radhika?
Pam, I wanted to ask, does the structure of the carbohydrate we choose to glycate affect these properties? So like a small sugar versus, and I also know we spoke about how small sugars can influence solubility, like salt.
Yes, absolutely. But in this case, in this example, we're covalently linking them via Maillard reaction type of reaction. So we don't tend to use small sugars because they have high rate, they're highly reducing sugar like glucose. So it has dextrose equivalent of 100, right? So it is highly reducing sugar. So when we try to glycate the protein with glucose, we cannot control Maillard reaction. So it goes very fast, and then it reaches advanced stages, which gives you adverse color and flavor and other, we call them advanced glycation products that you don't want. So we tend to glycate with larger carbohydrates, but also a very large carbohydrate, instead of enhancing solubility, might enhance gelation. So when you heat, then you have this bulky group, then you have gelatinization happening, and then you get formation of gel from starch, like kind of maltodextrin or starch gelatinization, and also, forming a gel rather than forming a soluble protein. So the size is very important, And also if you have branched chain versus a linear chain can also impact the characteristics of functional properties. So it's very important, the type of carbohydrate you use is very important in determining how the functionality is going to go.
Does it got to do anything with PDCAS value? Is it going to affect it in any way with like glycation or modification of the protein?
Yes. So now you're all interested in glycation. There's going to be a whole lecture on modification. But the digestibility, it depends on, again, if the protein unfolds or if the protein polymerizes. So there are a lot of literature out there that shows either enhancement in digestibility or reduction in digestibility. And it has to do with the degree of glycation and also the type of carbohydrate. Because if we enhance protein-protein interaction upon glycation, then we reduce digestibility. If we do partial glycation where we have partial denaturation of the protein, because we showed from the study that the protein partially denatures, so it opens up a little bit, but it does not aggregate. So we showed actually 9% enhancement in digestibility. So again, it depends on so many different factors. So either you increase the digestibility or you actually can decrease it.
Okay.
Very good questions. Okay. So yeah, I was going to move on without explaining this slide. So the effect when you have combined effect of pH and salt. So what do I understand here from this graph? So we have solubility and we have salt concentration. So if I just want to draw an imaginary line here, like where I'm pointing, and go across, I have the same solubility at different salt concentration. Why? Because the charge based on the pH impact at what concentration we're going to lose solubility. Because when you have higher charges, then you potentially need much more ionic strengths to precipitate the protein. Okay, so at pH closer to the isoelectric point, you need less salt to precipitate the protein. So this is what this figure is explaining, the relationship between having charge due to the certain pH and how that impact the amount of the concentration of salt that would result in a reduction in solubility or an increase in solubility. So effect of temperature on solubility. So usually thermodynamics. So you increase the temperature a little bit, you enhance solubility. However, well, there is an exception, which is beta-casein. It's the most hydrophobic protein in milk. So actually, when you refrigerate milk, beta-casein can leach out of the casein micelle and become soluble in the aqueous other way, kind of with the whey proteins. Why do you think? The question or the answer is in the question here.
Has to do with the decrease of solubility of the calcium on the milk? No.
Not really. So when you read this, the most hydrophobic protein in milk, hydrophobic interactions are weakened at low temperature. They are strengthened at higher temperature. So beta-casein is stabilized in the casein micelle by hydrophobic interactions. So at low temperature, these hydrophobic interactions are weakened. So some of the beta-casein leach out of the casein micelle. So that's the exception. So above 40 degrees, we start seeing even under the actual denaturation temperature, there's onset of denaturation and there's the denaturation temperature average of the protein. So at higher temperature, we start seeing the protein starts to denature. And as protein starts to denature, we see a decrease in solubility. So, but the temperature varies for different proteins because denaturation temperatures and onset of denaturation temperature is different among different proteins. So how do we measure solubility? So basically what we do is we prepare a solution. We can decide if we want to prepare in a buffer at a particular pH in the presence of salt. So we can change the, we can control the extrinsic conditions the way we want. And solubilize the protein, make sure that the protein is well wetted, well dispersed. And then what we do normally is we take a sample of this mixture, as much as homogeneous as we can get it. We determine the protein content in this mixture. We determine it either by Keldal, Dumas, not Dumans, there shouldn't be an N there. Dumas or calorimetric assay if we know that it's really a pure solution, there's no interferences, we can run assays like bisynchronic assay, BCA, but we need a standard. In this case, usually we use bovine serum albumin standard. But to have accurate results, we often do nitrogen-based analysis, which is, and Dumas is faster than Keldar. So we use Dumas to measure the protein. And then we centrifuge. We apply a centrifugal force to kind of precipitate the proteins that are not potentially soluble, that they just formed a dispersion, a colloidal dispersion, and they were not truly soluble. So they precipitate, and we take the supernatant and measure the protein content in the supernatant. And then we get protein content in the supernatant over the original protein before we centrifuge. We get percent of protein soluble. And that is kind of the, how we determine solubility is by getting that percent protein soluble. And we can, like I said, we can run it under different conditions. We can heat the protein as well to see impact of heating or thermal treatment on solubility, impact of salt on solubility, impact of pH on solubility. So we can do that as well. Moving on, gelation, which is another.
I have a question, sorry.
Yeah,
on solubility, like for example, if I make a solution, pass it through a filter, and then dry the supernatant, and then just do by gravimetry, would it be okay like this?
So you mean you run your solution by a filter, but you need to know what type of filter, what are you trying to filter? Are you
I assume that
aggregates?
Yes, then I'm retaining all aggregates and then I dry it. Do you have any
Not just not say dry it, you take the permeates, you mean?
Yeah, yes, sorry, yeah, the whatever passed through the filter.
You know, different proteins have different molecular weights. So choosing the right filter to do this could be challenging because a protein such as soy protein exists in quaternary structure of like 300 kilodalton, and it can still be soluble at pH 7 in this format. But then what do you do? What filter do you use? If you use filter that will retain the quaternary structure, then you're going to assume that it's not soluble. So no, so we don't do that for solubility.
Okay, thank you.
All right, so gelation. So basically a gel is a three-dimensional matrix, and it's formed by protein-protein interaction, as well as a balanced interaction with water. Because if you don't have water in the system and it's just protein-protein interaction, you form a coagulum, you don't form a gel. So a gel by nature is a three-dimensional matrix that entraps water. And there are different forms of gels. There is the jelly gel, the tofu gel, the hot dog gel, the egg gel, yogurt is a gel. So you have different types and forms of gels. Some are reversible, some are irreversible. So the water is the dispersed phase. It's dispersed within a continuous matrix, and the protein is the continuous phase or the dispersing phase. So we can form gels at different concentrations based on the protein. So gelatin, you can form a gel at 1% protein, but whey protein, you need at least between 5 to 10% to form a gel. Soy, you need 15%. PE, you need 20%. So it really depends on the type of protein. So that would dictate what concentration is needed to form a reasonable gel. So there's thermally induced gel and there's the cold set gel. But if we're talking about thermally induced gels are the most common gels. So yogurt, for example, is acid induced gel by basically reducing the pH to the isoelectric point, and then you get interactions and you form the yogurt that way. So let's talk about thermally induced gel. So what happens is you start with heat, and then when the protein denatures, it starts forming what we call soluble aggregates. And with more heating time, gradually the aggregates start forming a network. And that network is a balanced network in a sense that you don't get an aggregate, you have the water entrapped in it, and you get your gel with all the water that was in your system entrapped in that gel. That's the most ideal situation. And you have an impact of the temperature of forming the gel, the pH, obviously, what other solvents you have, whether or not you induce pressure or homogenization. So thermally irreversible gel, like the egg white, for example, is a thermally irreversible gel. And why do we get thermally irreversible gel? It depends on the type of protein we start with. If the protein is very large protein, above 60 kilodalton, and have over 30% hydrophobic amino acids, so a large percentage of hydrophobic amino acids, so we form really strong hydrophobic interactions. And we have high sulfidyl groups that will form disulfide interchange and then form disulfide linkages, basically, which are hard to break. So then we form irreversible type of gel upon heating. But then you have the reversible, thermally reversible gels. And the common example is our collagen. So collagen is made up of proteins that are stabilized by hydrogen bonding. And hydrogen bonding are destabilized by heating. And also electrostatic interactions are destabilized by heating. So you have more hydrogen bonding and electrostatic interaction than hydrophobic interactions. So when you heat, hydrogen bonding and electrostatic interactions are broken. So you get the proteins filaments solubilized and doing hydrogen interactions with water. So, and then when you cool, then random hydrogen bonding occur between these different filaments and you form your gelatin gel. If you heat, again, so these hydrogen bonding and electrostatic interaction will be broken, and then you get a soluble solution. Again, you solubilize your gel. So that is a reversible gel. It does not involve disulfide linkages. Once disulfide linkages are involved and strong hydrophobic interactions are involved, it's a reversible gel.
I have a quick question, Pam. For thermally reversible gels, is that infinitely reversible, or is that something that over time it won't reform a gel?
That's a very smart question. Why would you want to form a gel and dissolve it and form it and dissolve it again? So I don't know. I don't have experience with that to answer this question. If at some point the protein reaches its limit and tells you, leave me alone, I'm done. So it might. I never experimented with it or read about it.
Okay.
But it's a good question. If there is a limit to how many times you can form and deform, would be nice to experiment with, Leslie. Maybe you can bring gelatin and experiment with and
Okay.
tell us next time. Okay, good question though. I mean, I never thought about it. Okay, so basically your gel is a balance of attractive forces and repulsive forces. So you don't want to form your coagulum. You really want to form nice protein, water protein interactions. And then form your stable matrix, which starts with your native protein, the heating, the unfolding, the forming of the soluble aggregates through protein-protein interactions. And then with more time, you form the gel and you get your matrix. And then finally you reach your final matrix. And that's what it is. The properties that influence the gel formation or factors that affect gelation, properties of the protein. So we talked about molecular weight. So small molecular weight proteins don't necessarily form a gel unless you induce it somehow. So whey protein is small. It's like 14 to 18 kilodalton between the alpha-lactalbumin and beta-lactoglobulin. But the denaturation and the free sulfider group that is present in beta-lactoglobulin allows the formation of a stable matrix. And this one sulfider group allows the breakage of other disulfide linkages. Then you get more free sulfider groups, and then you get more disulfide interchange. So that's kind of an exception. It's a small molecular weight protein, but it has other characteristics that induces the gel formation. Composition. If you have high hydrophobic percentage, like we said, it tends to form irreversible gels and possibly strong gels. So, and then surface charge. If you have high surface charge, you have less potential to form protein-protein interactions. So sometimes if you have a protein that is very high in charge, maybe you want to adjust the pH to a pH that reduces this charge, or maybe add a little salt to also reduce this charge too. We talked about hydrogen bond and electrostatic interaction. So if you have protein stabilized by these types of interaction, you form reversible gels. And when you have high hydrophobicity, you have more interactions upon thermal treatment. So you form stronger gels. And we talked about disulfide role in formation of the strong gels, and how with temperature and high pH, the higher the pH, the more the disulfide linkages can occur as well. Also, you have interactions with different proteins. So if you want to take a one-way protein, alpha-lactalbumin, try to form a gel, it forms a really less elastic gel, less strong gel. But if you add beta-lactoglobulin have that free sulfidyl group that alpha-lactalbumin does not. It does have disulfides, but it doesn't have that trigger to form disulfide interchange. And the trigger is the sulfidyl group. So that's why a combination of beta-lactoglobulin and alpha-lactalbumin forms a really nice gel. So mixing the both proteins form, that's what I meant, forming better gel. Also interaction of different proteins. So sometimes in the formation of yogurt, they add a little bit more whey protein to yogurt. Why? Because when you heat and you pasteurize and then you try to form the gel, to set the gel, whey protein have this free sulfidyl group. It can interact with kappa casein by disulfide linkages and strengthen the gel. So that's why some yogurt formulation, they add whey protein to it. Environmental condition other than the protein characteristics. Protein concentration, we talked about that. So depending on the type of protein, you need certain minimum concentration. We call it least gelation concentration. Every protein has its own least gelation concentration, the least amount of protein that will actually form a gel. And then sometimes you don't want to form a gel at the least gelation concentration because the gel might be weak. You try to form the gel at a little higher concentration so that you have a stronger gel. In terms of pH, so at extreme pH, you have really high net charge. So you form a solution, and no matter how you heat it, it's just the proteins are not going to interact with each other because of same charges, a lot of repulsion. So you want the pH not to be very acidic or very basic. You want it to be not at the isoelectric point either, because then you form aggregates such as this kind of gel, turbid gel. So you form aggregates rather than nice network. So pH is important. What pH? It depends on the type of protein. Different proteins might, one protein with pH 6 would be better, another type of protein pH 7 would be better to form a strong gel. Same with salt. So a little bit of salt sometimes help form a gel. A lot of salt can cause aggregation, and maybe very small concentration of salt can enhance solubility and reduce the gelation. So basically, we want to be careful in the choice of our conditions and take that into account when we're forming a gel. So that's where formulation of different food matrices plays a role. How much salt we can add, and what pH we can use, and what carbohydrate is going to be added to influence the gel formation, and so on.
Pam, I have a question with acid or pH. So when I do acid gelation, I got to do it slowly, or I got to add GDL, which also does the same thing to milk proteins. So why is that we need to slowly decrease the pH to get it to gel?
Yes, because if you decrease the pH suddenly, and this is, I was going to talk about heat here in a minute. If you change the condition abruptly, then all of the proteins are going to lose their charge and they're going to aggregate rather than form a gel. So you want to slowly get down to that pH so that you induce gradual protein-water protein interaction. It's same with heating, and I was going to explain that in a minute. So it's, yeah, you don't want aggregation to happen. You want it to be a nice formation of soluble aggregates to then a network of that aggregate, and then a complete stabilized network. Any fast change that might cause protein-protein interaction, you will get an aggregate rather than a gel. Okay. Calcium ion. So calcium ion, like if you think about cheese, sometimes they add calcium to milk to form the cheese to enhance the yield, because calcium helps form the calcium phosphate bridges between the casein. But also in tofu making, they add calcium because that enhances the gel from soy, so that, which is the tofu gel that is formed. So calcium, because it's a divalent, so it can bind to one negative charge on one protein and another negative charge on another protein, forming that ionic bridge. So it is also added to enhance gelation. Heating temperature and heating rate. The heating temperature is, so you want to heat the protein to above its denaturation point. So if you have a protein that denatures at 90 degrees and you're trying to heat it at 80 degrees, it's might partially denature, but not enough to form the gel. So you really need to make sure that you heat it above the denaturation temperature for the right amount of time to cause denaturation and then formation of protein-protein interactions. Heating rate, which is very related to the drop in pH. So you don't want to increase like suddenly have very high heating rate that will actually denature and quickly form the protein-protein interaction and less protein-water interaction. So heating rate is very important. It's gradually increasing temperature and gradual denaturation and gradual formation of protein-protein interactions. Proteolytic enzymes, so we want to make sure we don't have endogenous enzymes that would break up our proteins. So smaller peptides have less tendency to form stable and strong gels. So, and the common example I give is if you want to make a jelly with pineapples, you don't want to use fresh pineapple because pineapples have bromelain, which is a protease. So you want to use canned pineapple if you ever want to make a jelly with pineapples. Polysaccharides and sugars. So again, you can enhance gelation by, interaction with polysaccharides in there. So, but a little bit of sugar can enhance solubility rather than formation of a gel. But high concentration of sugars or certain polysaccharide can actually aid in the formation of the gel. So I want to link now structure to function. And here is looking at protein gelation and molecular weight. So this is camelina protein. We work on it in the lab. And camelina protein, when you run it on a gel, you see that its individual peptides or polypeptides are really small. So they're like 25 or less. And then if we compare it to soy protein, you really have high molecular weight proteins here, close to 100. And these are only the monomers. They do form larger molecular weight quaternary structures, but the monomers themselves are larger in molecular weight. So if we look here at gelation strength, don't worry about the different treatments here, but if I look at any of these treatments, there's all alkemarina proteins, they all have less than half the strength of gelation of soy protein. So I'm linking this now to the molecular weight, okay? Here, we have soy and we have pea. They have kind of similar molecular weight distribution. They do have some high molecular weight proteins and low molecular weight proteins, but maybe soy have more high molecular weight protein. But what I want to point out is not just the molecular weight difference, is the type of protein that is in there. So soy protein is not made of one protein. We will learn that when we cover legumes later on. But it has different types of globular proteins. It has what we call legumin and viscillin. In soy, legumin is glycinin. It has its own name. And beta-conglycinin and gamma-conglycinin are the viscillin-convicillin in pea, the counterpart. But if we look at the glycinin, it's much present at much higher concentration or higher percentage than legumin, which is a similar type of globulin in pea. And why is this important in terms of gelation? Because glycinin has the sulfidyl groups. The legumin, that is, also has the sulfidyl group. Viscillin lack sulfidyl groups. So if we look at the concentration, least gelation concentration for soy is 10, but it forms a nice gel at 15. But for pea, it does not form gel at 10%. It forms a weak gel, if even, at 15%. But if we want to form a nice gel of pea, is at 20%. So these are different types of proteins that, if we want to look at gel strength, whey protein forms a really nice gel, strong gel. Why? It has this free sulfide group that kind of is the catalyst for disulfide interchange. Soy protein isolate is next. Fava bean, pea protein, rice proteins, never mind, don't form a gel. So different proteins, different structure, different function, and therefore different gel strength. So formation of protein-protein interaction is important when we talk about, which is a very common now market trend, is it's cheese alternative, so plant-based cheeses. So you really want to form this gel-like strong texture of a cheese, and plant proteins don't form that. This is the CLSM image. And CLSM image, you can see the protein stains as green, the fat stains red. So there are certain dyes that you use. So you can see the red as oil droplets, the green is the protein, and the blue is the carbohydrate. So in vegan cheeses, you see the green, they're just there. So they don't form a network, the plant proteins. They don't really, they're added just to say we have protein in the matrix. And what's forming your matrix is really your carbohydrates, your gums, your hydrocolloids. These are forming the matrix. So most of the starch, so most of the composition of plant-based cheeses are starches and gums and a little bit, tiny bit of protein and some oil is in there, obviously. So looking at cheese, you can see the green texture here of the cheese. So this green here is the protein matrix. So you see very nice protein matrix distribution and very nice distribution of the lipid in that cheese, which we don't see in plant-based cheeses. Lastly here, before I quit, I want to finish gelation and then I'll stop. So how do we measure gelation? Usually we look at water holding capacity because it's important to form a gel that does not synerese. So we look at water holding capacity. We form a gel in a tube, we invert it, and we measure kind of the change in weight based on the loss of water. And we calculate water holding capacity. So it's important. This is kind of an application when you have beef patty and a beef patty supplemented with whey protein. So when we supplemented the beef patty with whey protein, we got more water holding capacity. We enhanced gelation, we enhanced holding of water. We got less syneresis. If you want to determine water holding in an actual product like meat, we can do that. So we did that actually in one of our projects that looked at incorporating a whey product into meat. So you grind the meat, you have ground meat, you measure fat and moisture content, you cook it, let it settle overnight, and then you'd see the separation of water and oil, and you can determine the loss in water and the loss in oil and the impact of adding a whey protein product into it and how that enhances, reduces the separation. Then we look at gel rheology. So you can either do, the stress strain modulus of elasticity, J prime, G double prime, or most commonly in the lab, we use texture analyzer to determine gel strength. So we form our gels in small centrifuge tubes, and then we use the texture analyzer with a specific probe that basically goes down and presses the gel until deformation. And we measure the weight and we convert the weight to the force, which is the force needed to cause a gel deformation. And that would be our gel strength in Newton. We convert, by using acceleration, we convert mass to Newton, to force. And stopping point. All right, I will finish this next week and start enzymes next week. Thank you guys, and I will see if you do you have any questions? Anything at all? Okay, then I will see you guys next week. Bye-bye.